So today we had a couple of student submitted questions. I think we'll do it in order of easiest to address right now, which will be about why does the plus c constant of integration not matter for area under a curve. I gave a written response to it, but I think a visual might further hit it home so we're all clear on what's actually going on. So to get our heads around this, let's just imagine we have some function f of x. Let's say we have some quadratic f of x, and we want to find the area under the curve between, let's say, here to here. So we want to do all of this, and all of this. Whether we want to do signed area or total area is redundant, because it just changes how we find the area, not whether or not the plus c is going to matter for it. Now, the assumption that I'm making where the issue is if you think about adding a plus c to this function, that is a vertical shift. Could be up or down. Alright, let's say we're shifting it down ever so slightly. Let's say we have f of x minus 2. We're shifting it down even more. And let's say that the new x-intercepts cut off that bit entirely. Suddenly we only have this piece of area, not any other piece of area. Not any of these anymore. So why is it that when we do definite integrals to find our bound area, why is it that the plus c's always cancel out when we can clearly see that adding some constant, some vertical translation, does visibly change the area? The reason why comes about when you try to identify what you actually do to find bound area. The steps of finding bound area are as follows. First, you antidiff to your f of x plus c, and then you do your terminals. So let's say this is 2 to, oh sorry, other way around. Minus 2 to 2. Where was I going with this? Oh yeah, and then you put in your terminals. So let's say this plus c is already included inside of capital F of x. You now do your capital F of top, which is 2, minus capital F of bottom, which is minus 2 in this example. And again, just assume the plus c was already in there. I just didn't want to redefine a new function that had the plus c already in it. The reason why I'm highlighting that is because the plus c never actually makes it onto this original function. You never actually have a scenario where a constant could shift this thing up or down. What you are shifting up or down instead is the capital F of x, which in this case would be some sort of cubic. You have your cubic, and this can be shifted vertically up or down infinitely depending on what your plus c is. The reason why this doesn't matter is because you are no longer trying to do the bound area under this thing anymore. You are simply doing a subtraction between two values. And because of that, the plus c's will always cancel out. Does that visual demonstration make sense? I think you said something, but it didn't come through. Yeah, okay, cool. Okay, so this looks like the whole cohort for today, so I don't know if you can already tell. The last, we'll say 4 days or so, I've been dealing with flu. that has been wrecking me quite a lot. I still feel like I'm doing maybe a decent enough job explaining things. Just a heads up that if I am writing things that don't make sense, it might not be your fault, it might genuinely be my fault. I might be a bit slower than I usually am. I might make silly mistakes that I otherwise wouldn't. So definitely try to keep me honest here. It's not at all offensive if you jump out and say, hey, you kind of did this wrong. Okay, just give me a sec so I can not be as hot right now. And I'm probably also going to take a lot of drink breaks. Okay. The next question up was 14H question 1. Don't know if we have the same work solution, but I'm confused on why some graphs are like this. Why does it not start from 0 or just use the periods normally? Also, the cos questions are confusing. Yep, fair enough. I did have a look at this ahead of time, and you're absolutely right. They could entirely start at 0. There's truly no reason not to. It's a bit easier to start it out where the horizontal translation is, because you're doing less work, because essentially whatever this term is tells you where to start, and then everything else is the same from that point onwards. Whereas if you're trying to start at 0, you now have to retroactively figure out what 0 is, and you'd have to start your equations by solving f of 0 to know what the xy coordinate is. So if we do the first cosine one, just to give a demo, because you mentioned those were quite tough, I'll just give you a hypothetical as to how you could do it. So they always start at 0, which is again valid, right? One complete cycle can start literally anywhere. Okay, so this is y equals 2 cos bracket 3 bracket theta plus pi on 4. So if you really wanted this to start at 0, the first thing you would do is try to figure out what the y value is at x equals 0. So you want to solve for y of 0. That is therefore going to be 2 cos 3 0 plus pi on 4. Was there a... Okay, there's no vertical translation. That's fine. Okay. This is now going to be 2 cos 3 pi on 4. And cos of 3 pi on 4, I'm not going to give that one away. Can anyone tell me what cos is at 3 pi on 4? Yeah, I think you're still having a bit of audio issues, unfortunately. I'm fairly certain you would have got it though. This is going to, yeah. It'd be negative in this case actually, because of on the left hand side, 3 pi on 4 gets you to here, which is on the left hand side of your x-axis. But yeah, the coordinate itself is the root 2 on 2, 1, just going to be negative instead. So that's going to be 2 times negative root 2 on 2, negative...
Right, it's working now.
I can hear you now. Yeah, that's good.
Yeah. Isn't 3 pi on 4 like the same as negative pi on 4? So
Is
wouldn't it
3
be
pi on 4
square
the
root of
same?
2 over 2? Oh wait, no. Wait, no. Yeah,
no, not quite.
Yeah.
Yeah. Yeah, okay. Cool, so the fact that we get a nice-ish final answer, well, I guess it's not too nice, because really it's not really one of our key features, but, you know, it's something. So if we wanted to start this one out at 0, the starting location of this would be at 0, but now down at negative root 2, because this is your y value when you shove in x equals 0. Then from here, yeah, you could just do a full period from exactly 0, which is really easy, because you just take the n term, capital T equals 2 pi on n, where n is 3, which means the end of this period is going to be 2 pi on 3. The challenge in doing it this way is that you can no longer half and half again to get your spacings out. And the reason why is because this is not one of the key features. I mean, it's technically a key feature in that it's a y-intercept, but when I mean key features of the circular function, I mean peaks, troughs, mid-levels. If you look at what the graph is, the amplitude being 2 means we should have a peak of 2 and a trough of 2. And so where these are going to be located is no longer going to be at quarter period intervals if you start at 0. We can... I don't think it's worth finishing this way to do it, because the reason more or less why I brought it up is to say, yes, it's theoretically doable. The way you would go about it would be to literally force solve where these spots would be. Like if we know there's a peak of 2, we can say, well, hang on, what if I just set my y value equal to 2 and then just solve for theta? Whatever that comes out to be, bang, I've now got the peak that I wanted. And then you keep going over and over again. And if you know anything about how long it takes to solve circular functions, you'll probably quickly realize that it's a pain in the ass to do so. So that's a bit of an explanation as to why you wouldn't want to do that. Is that fair enough so far? We'll move on to doing it the proper, well, the easier way. Okay. Okay. So, actually, maybe I could just... No, it's fine. I'll just copy it down again. Okay. So we had y equals 2 cos 3. I know it's a bit blurry right now, I'll just finish writing it up before I fix it. 3 theta plus pi on 4. Oh, that's right, yeah, it's brightness, not misfocused. There we go. Ah, really? I thought I had it. Seriously? Oh, God. Maybe a little bit less. There we go. So, my preferred way of doing this is kind of written in my notes, but not fully. And the genuine reason why I don't have the best way to do it written in my notes is because I haven't yet to find a way to explain it properly in text, in a way where people don't consistently ask me questions over and over again of what do you actually mean by this step. I think I've got videos attached to this document that that explain the best way to do it. But the good news is you get to see it live, and the recordings will... Oh, hang on, I did not post the recordings, did I? Sorry guys, yeah. Okay, I'll post the recordings today. But yeah, when the recordings for this one come out, you'll be able to watch these back. But okay, so most of this is good. First step, just find the period. Nice and simple. We did this already. Capital T equals 2 pi on n, where n is 3. From there, let's get our peaks and troughs. Again, we saw that already. Plus minus 2 are our peak and trough values. Step 3, dividing the period into 5 equal x coordinates, is a handover from when you could just go 0, 2 pi on 3, half, half, and then backfill. When you have a horizontal translation, you're essentially shifting all these things forward, which is what I've written in the notes. The reason why it's not effective to do that, even though that's what you are technically doing, is because doing a calculation 5 times in a row is a waste of time, more or less. So a more efficient way of achieving the exact same result is to now start by looking at what your horizontal translation term is, and this becomes your new starting point. So this is a plus pi on 4, which means we are shifting left by pi on 4. So we're going to have our plus minus 2. We're going to have our starting location just roughly penciled out as minus pi on 4. Don't be too married to this one here, because depending on how the spacings work out with the period, you might find that you need to spread or fit more intervals in here. So it's usually a better idea to just, lightly pencil this out, just so you've got a rough idea of where it is. If you want to even further, you can also look at the cosine itself and be like, okay, well, cosine always starts at a peak, so if this is my new starting location, then this should be a peak. But yeah, these are things you could easily rub out if you need to slightly shift because you didn't give yourself enough space. So, how do we achieve the same result without doing so much calculation? We start by finding the quarter period. So we're still going to do essentially our half and half again to get our quarter period. So halving that down goes to pi on 3, halving that again goes to pi on 6. Normally that was enough to just be like, cool, pi on 6, pi on 3, whatever the other one is, and then 2 pi on 3. But because we have a new starting location, we can't really just make use of that. What we can do is, again, make use of the same concept, which is to say, hang on, all the key features of our sine or cosine are separated evenly by the quarter period. So if it starts here, then plus pi over 6 to the right will get me my next key feature, which in this case should be a mid-level, which, because there's no vertical translation, will be on the x-axis. It'll be an x-intercept. So we take our starting location, negative pi on 4, and try to add pi on 6 to it. There's a bit of fraction math involved here. I will also show you a way to remove the amount of redundant math that you have to do for this sort of thing. You only need to do the conversion to get same denominator once. So we do our cross multiplication. So this is going to be negative 6 pi, and this one's going to be plus 4 pi. Actually, maybe I'll make it even clearer and make them two separate things. yeah, cross multiply, so that's going to be 6 4 is 24 plus 4 pi. So these two things are equivalent now. That'll come important later. All we do now is complete the easy math, which is just 4 minus 6, essentially. So negative 2 pi on 24, which I will not simplify for a good reason. Just let me give a drink. Okay. The reason why I will not simplify this further is because I've already done the work converting a nasty denominator into one that is much more easier to work with. And so if I simplified this down to negative pi on 12, suddenly I'd have to try and simplify this one down, and I'm just doing redundant work. Whereas if you look at what's going on here, I know that these are the same thing. Pi on 6 and 4 pi on 24 are the identical thing. So if I keep my denominator as 24 the entire time, literally all I have to do is keep adding 4 to the top on this. That's it. So I only do the... It's not particularly hard, but it's just, you know, a step that you have to do. We are minimizing the amount of times you have to repeatedly change the denominator. So because this is 4 pi on 24, and this is our next key feature, we now start at where we left off, negative 2 pi on 24. If again we add a quarter period to that, we're now going to have 4 plus negative 2 for positive 2 pi. Oops. 2 pi on 24, and then again add another 4. 4, 5, 6 pi on 24, and then just keep counting until you get 8 values. Oh, not 8 values, 5 values, which includes this one. So you got 1, we got 2, we got 3, we got 4, 1 more left. Adding another 4 gets you 10 pi on 24, and only here will I bother to simplify everything down. Negative pi on 24 becomes negative pi on 12. Positive 2 pi on 24 becomes positive 2 pi on 12. Again, you can see how already I've still squished up a little bit. So let's give myself some more space. Where do we start again? Minus pi on 4. Let's go here-ish. Yeah. Minus pi on 12. Positive pi on 12. 6, so that's 3 pi on 12, which is then pi on 4. This one ended up being quite nice, symmetrical about the x-axis. Pi on 12, and then lastly 10 pi on 24, 5 pi on 12. So finally we just dot out what we had. So again, cos always starts at a peak, so if negative pi on 4 is our starting location, then we're going to put a peak there. From there, the next should therefore be a middle, which is why we're going to put a dot here. Then there should be a trough at the next thing, so we do that. Then a middle, and then finally the peak again. Cos graphs tend to always look like V's. Try not to actually draw it as a V. Try to give it some curve. pretty much almost done here, but I'll just take a quick pause there. Was there anything about any of that that needs further clarification? How can you tell the line curves like that? Yeah, so I am basing my decision off of the generic, with no transformations at all, the cosine or the sine, depending on which one I have. Yeah, exactly. It's because it's a cos graph, right? So if I think about what the graph of cos looks like, its starting location is by default 0 because it has no transformations at all, and its starting location is a peak. If I had negative cos, then I'd be looking or reading into my mind about the negative cos graph instead and being like, okay, well this time it's now a negative one instead. And as soon as you know if you have plus or minus cos and where that would therefore be, cos specifically is actually quite chill once you have that, because it always starts at a peak or a trough, which means your next spot is always a mid-level. And it's pretty hard for you to go peak, mid-level, and then go back to peak, right? You'll realize your graph looks pretty wonky because you've got too many values and you've suddenly drawn too many cycles. But yeah, so basically it's just because it's a cos graph. I'm looking at the generic versions of them with minimal transformations, such that it tells me what the overall shape is going to be. The only thing that's different is going to be, the only thing that's different is going to be the x locations of those spots. All good? Awesome. Okay. Did we want to practice at least one more of those, or are you happy enough to start tackling those yourself? One more? Yeah, absolutely. Still a cos again, or maybe a sine this time? Fine with any? Sure. Let's have a bit of variety then. Yeah, let's make sure we're putting in at least a horizontal translation. Let's go with part D. Okay. Yeah. Y equals root 3 sine 2 theta minus pi on 2. Cool. Okay. Just give me 1 second while I turn off the heater. I'm starting to sweat. Okay, so similar procedure as before. Does anyone want to try and help out? What do we need to do to sketch this graph? One of the things that's going to be important is getting all the key features, y value, just the key features of our circular function. So we're talking things like getting the period, peaks and troughs, these are some quick and immediate things we can get. How do we get the period in this case?
We look at the amplitude.
That'll be for the peaks and troughs, the amplitude.
What did you ask?
Yeah, I was asking you about the period. And
Oh,
yeah, Haley, that's
I
right.
missed it.
Yeah, which is 2 pi divided by 2, which is just the end term. Yeah, I'm sure you just misheard me. That's fine. But yeah, good job. This will be capital T equals 2 pi divided by n, where n is 2. Therefore, period is pi. Peaks and troughs, Nihal mentioned, which is looking at the amplitude. Because there's no vertical translation, it is just going to be plus minus whatever the amplitude value is. So plus minus √3. Next up, when it comes to things with horizontal translations, what we do is we say that this is where the starting location is going to be. Again, it doesn't have to be there for those who joined afterwards, but when this recording goes live, you'll see, for those who joined late, why it's impractical to do anything other than set this as your starting location. So, if this is our horizontal translation of minus pi on 2, that means we are shifting right by pi on 2. What do we do from here to get the rest of our interval ticks? If you think about how you normally get interval ticks without a horizontal translation, it was all about just finding the period, which in this case is pi, and you'd quarter it up, essentially. What that tells you is that all the key interval ticks are separated by a quarter period. So if all the key interval ticks are separated by a quarter period, and we know where we're starting, how might we get the next one? Okay, so if everything is separated, or the interval ticks are separated by a quarter period, it means we should probably start by finding out what that quarter of a period is. So we want to quarter pi, which is nice and easy. It's just going to be pi on 4. Pretty sure. So if everything from here onwards is separated by an additional pi on 4, it basically means I'm just going to repeatedly add pi on 4 over and over again until I have my 5 ticks. So I take my starting location of pi on 2, I add my pi on 4. Technically I can subtract, I can go backwards, but subtraction is typically more annoying to deal with than addition. From here, we're just going to do our conversion, which is actually easier this time because this one you just multiply the top and bottom by 2, giving you 2 pi on 4 plus pi on 4. Yep, that's good. And so in this case it didn't even need to, this one didn't even need to change. But it does make the further additions really easy because you are literally just adding 1 to this value every single time. Which is going to get us, excuse me, 3 pi on 4. Sorry. Oh god. This is now our second interval tick. That's going to get us 3 pi on 4. Okay. And because we are now having same denominator the entire time, adding pi over 4 to this repeatedly is now really easy, because you are literally just adding 1 over and over again. That makes the next one 4 pi on 4, 5 pi on 4, 6 pi on 4. Is that enough? It was 1, 2, 3, 4, 5. Yeah, cool. Only now will I bother to simplify things further. So 3 pi on 4 we already drew. 4 pi on 4 is just pi. Five pi on 4 stays as is. Six pi on 4 goes to 3 pi on 2. Okay. Maybe you'll have to forgive the spacing on that a little bit. Yeah. I guess the other advantage of being able to set your own scale, if it just says complete one cycle, which all these questions do, they just say, well, at least question 1 does. If you move away from the y-axis, you now don't have to find your y-intercept. Now, it's not particularly hard to do so, but it is technically one less step, so you can be maybe a bit, well, it's a nice little bonus. I don't think it's worth, you know, if you had a starting location over here, I don't think it's worth dealing with negatives the entire way through just to not find the y-intercept. So it's just a nice little bonus when you have a forward shift. And then yeah, from here, sine always starts the middle regardless, so that's easy. Doesn't matter if it's positive or negative. From there, whether it goes to a peak or a trough is going to depend on the graph, whether it's got a reflection or not. This graph has no reflection, so if we look at the generic sine, we can see that immediately after its starting location of the middle, it goes to a peak. So the next value that we write is going to be the peak of this thing. It's about this time I should probably write out what those peaks and troughs are, which we saw earlier, plus minus the amplitude. If there was a vertical translation, things would be a bit different, but this is predating vertical translation stuff. Yeah, and then the rest of the pattern becomes quite simple to follow. From a peak you have to go to a middle. From a middle you therefore have to go to a trough. From a trough you have to go to a middle. And when all is said and done and you've drawn up your graph, again, you'll have to forgive the spacings on that. It should look like a complete cycle. So let's say you accidentally forget your troughs, right? Like let's say you go, cool, it should be like this, and like that. Let's say you mistake these and just go from middle peak, middle peak, middle peak. Suddenly it looks like you've drawn 2 cycles, maybe a little bit less. That's an indicator to say, hey, you've done something wrong. Either your scaling's wrong, or you've just not dotted out things properly. Okay. How's that? Any questions at all? Okay. It's not chapter 14. I think it's chapter... where is it? What is it? There's one that's a chapter review on exponentials, logs, and circular functions. So let's see if we can suss that one out. Oh, it is chapter 15. Let's see how we do. 529. We've done a little bit of circular function stuff already, so maybe we'll touch on some of the logarithm stuff, or logs and exponentials stuff. So we'll skip this one a little bit, and just go straight to question 2 here. I'm sure it's been a while since you guys have done questions like this. Actually, no, this one's not too bad. You're actually given the function already. In some cases, they ask you to solve for the function itself, and that's where it gets trickier. Once you're given the function, usually analyzing that function's quite trivial. Usually, anyway. Okay, we got some bacteria, and yeah, bacteria versus time. It is exponentially rising. Question A, state the number of bacteria present at the start of the experiment. So we have our function n of t. Oops, I need to hit define first. We have our function, which is 40 times 2 to the 1.5t. Obviously I'm going to be using x instead, just in case I want to graph it. Number of bacteria present at the start of the experiment. This is a function which has number of bacteria on the y-axis and time on the x-axis. So if I want to know the number of bacteria, I want a y value. And if it's at the start of the experiment, that's going to be t equals 0. And it's not really properly defined here. Just after t hours. Usually they would say t hours after the start of the experiment to be a bit more airtight with their wording, but it's a pretty safe bet if there's no other things that would I don't know the word right now. If there's nothing that contradict. If there's nothing that would really contradict that, it's a pretty safe bet to say t equals 0 is going to get you the start of any given scenario. So when all else fails, you can just put this in your CAS or even solve it tech-free, right? What you'll notice is that you get the answer of 40, which conveniently is the value that is at the front of that of the front of the exponential. The reason why, if we think about the arithmetic that would be done, you start by shoving in your t equals 0. That means your exponent goes to 0. You now have 2 to the power of 0, which is 1. 40 times 1, 40. So this will work every single time, so long as there is no vertical translation. Because if you did have like a plus c or whatever in here, then yes, this would disappear, but you'd still have a plus C just chilling there. So that's why I show you the generic way of doing it always. Worth pointing out though, I've pretty much never seen them put a vertical translation in there. In terms of how you write this answer properly, I think it's fine to just give the number. Yeah, I don't think you need to say bacteria specifically. Part B, state the number of bacteria present after 2 hours, 4 hours, 12 hours. This is effectively the exact same question as part A. You want to find a Y value, the bacteria, and you're given some T values to work with. Start is just another way of saying 0 hours. So we would do the exact same thing for each of those values. H of 2, H of 4, H of 12. And it's kind of cool to see just how quickly these things can grow. Sketch the graph. Yeah, that's pretty... CAS is too easy for that sort of thing, so I think we'll just revise how to do it tech-free. Okay. So, exponentials. One of the first things I'm looking for is where my asymptote is. The asymptote is always given by the vertical translation, which in this case, we talked about before, is just 0. So my horizontal asymptote is just the x-axis. From there, I'm just looking at whether it's a positive or negative exponential and what the base is. The reason why I'm specifically looking for the base is because a base between 0 and 1 has different behavior to anything outside of that. The base between 0 and 1 is quite rare to come across, but it's a thing. You're effectively getting a reflection in the y-axis, and I'll show you what that looks like and why it is the way that is. Okay. Exponentials, graphing exponentials. So if you think about how the exponential works, you've got basically more or less this kind of shape, right? You shove in some x values and every incremental bit in x is going to, in this case, double the y value every single time because the base is 2. That's why it increases quite rapidly on this side, and that's the same reason why it decreases quite rapidly on this side, because when you start getting negative numbers, those are flipped to fractions, and now your denominator is getting rapidly bigger over time, but never actually hitting 0. So the reason why having a base between 0 and 1, let's say a half, hypothetically, is that you've now effectively got the opposite behavior, where positive increases in the x, in the exponent, just keep increasing the denominator on the fraction, right? Because if you square the top and the bottom, the top is always just 1, right? But the denominator will keep changing over time. And so that's why what you effectively get is a reflection across the y-axis. So definitely worth looking out for whether you do get a base between 0 and 1, because it might happen and it does have an impact on the graph. Again, pretty rare, but worth pointing out. We do not have this. In fact, we have the same graph we saw earlier. It's just base of 2. So we know already it's basically going to look like this. The coefficient at the beginning basically matters 0, and same with the coefficient on the t. it's functionally useless because the shape is going to be more or less the same, and the reason why is because we set our own scale. Right? These are things that stretch the graph, and so if you just set your own scale differently, you can make the graph look like whatever you want, more or less, as long as it looks like an exponential, of course. But yeah. So yeah, only remaining key feature is going to be our y-intercept, which of course always solved by x equals 0. Capital N of 0, which we already did, right? That was the answer to part A. But I guess I'm already here, so I might as well show the arithmetic in more steps. 40 by 2 to the power of 1.5 times 0, which gives you 40 times 2 to the power of 0, which gives you 40 times 1, which gives you 40. To be really pedantic, oh sorry, not pedantic, but accurate, you now need to, once you have your valid graph, look back at the scenario and see if there's anything about this particular scenario that causes some parts of your graph to be invalid. Does anyone want to take a stab at what we probably should do here to make this graph more accurate to what the scenario is actually talking about? Have a read of the background. Think about the valid domain of this graph. Have I drawn too much? Where is an appropriate spot to actually cut this thing off? Okay, so a good spot to cut this one off would be at t equals 0 and shooting off towards the right hand side. And the reason why is because the start of the experiment is considered t equals 0 here. And so pretending that we can track things prior to the experiment starting is not a great idea. We can model it if we can understand that the growth is roughly exponential. Like in the real world you can, it's called extrapolation. Yeah, it's called extrapolation, which is you have a limited data set and you fit a model to it. In this case you'd fit an exponential that hits most of the key features, or just like roughly getting the shape right. And then from there, because you now have that mathematical model, you can plot that over whatever domain you'd like. And just as another bit of trivia, there's the other thing called interpolation, which is mainly around when you have gaps in your data. This is when you're graphing data things. Same with the other one, of course. If you could just graph the function, then obviously you don't need to fit a function to it. So like, you know, if you have your dot, dot, and let's say you're missing that dot and it goes up here, interpolation would be saying, okay, curve of best fit is roughly exponential, and so if my curve says this connects most of the dots, then I should expect a dot here. That would be considered interpolation. Okay, cool. Next up, part D. How many minutes does it take for the How many minutes does it take for the number of bacteria to double? Pay very close attention to the wording on this one here. It's a time value, yes, but it's minutes. So far, the t values that we're working with have been hours. So it's not just asking us for what t does our bacteria double, it's then going to require us to convert to minutes. So how are we going to do that? Well, there is one way, which is to just sort of guess and check your way through it. Actually, not even guess and check your way through it. You can just cas solve through it and just brute force it that way. It requires like a minimal understanding of the function itself, and you just go, yep, cool. I know I'm starting at 40, double of that is 80, so if I just solve what time value gets me 80, awesome, 2/3. This is 2/3 of an hour, so to convert that to minutes properly this time, you've now got 40 minutes there. And it doesn't actually matter what 2 points you use. Exponentials grow at the same rate always. They grow at the rate of the base. So you could have chosen the 2 hour and 4 hour thing that we found in part B. You could have chosen the 4 hour, 12 hour. Wait, sorry, hang on, what am I saying? You could have started at a later spot. So like, let's say you use the starting point of the 2 hour one. What was that? 2 hour got us 320. So we just copy that down so we still have it present. And if you really wanted to, you could now say, okay, cool. 320 doubled. Huh. Why is that a bit different? Oh, that tells us the actual x value. Yes, the actual time value, not how long. If you wanted to then revert that back to the actual time between the 2 points, you would now have to subtract the 2 that you started with. So 8 on 3, subtracting 2, which is no longer something you would want to do, because this is just making it more complicated. Not that it wasn't more complicated to begin with, do it this way. More so just exploring what you can do with these sorts of things. Okay, cool. We're about to hit time here, so I guess if there's any questions at all, feel free to let me know. Happy to stick around for a little bit, and I'll do my best. Otherwise, thank you for coming. Cheers.